So we were on the pseudo random number generation last time, and we talked how simple the generators are. Generally, just linear congruential means you just multiply a number, add a number, and you get a different number which is random. They pass all the randomness tests, and then we have BBS generator, which was actually somewhat more random, which was actually better because you couldn't predict it. As opposed to LCG, with LCG, the problem is that given two or three numbers, you can figure out what the seed is, what the multiplier is, what the adder is, and therefore you can predict the rest of the stream. That's why they call pseudo to begin with. Then we talked about pseudo random function. Why you say value? PRS. Pseudo random function and pseudo random generator. So random number generator, according to the book, the difference is continuous stream and just getting a number. With this one, you just get a number, let's say a key, and you're done. And with this one, you keep getting the stream. So basically, you keep feeding back the seed, and you keep getting the numbers and numbers and numbers, and then you just get a whole series of zeros and ones that you can use to encrypt. So there are several ways to do this. One way, and now the numbers that we're going to talk about are pseudo-random numbers, but they are going to be secret in the sense that there is a key here, which if somebody doesn't know, then they cannot generate the same stream. Only people who have the key can generate the stream and therefore decode whatever we are encrypting. So these are different from LCGs in that sense, right? In LCGs, only thing we have is a seed and the formula, and the formula is easy to calculate. Here, even if you get thousands of bits, you will not be able to calculate the key. All right, so the way we can generate these streams is just by using block ciphers, as we saw. So for example, you could take any of the block ciphers. Can you remember one or two of the block ciphers? Anybody? We talk about many standards. AES and DES. Right, so those are block ciphers. You can use those, and all you do is you take a number, encrypt it with your key, and you get a random number. And then you keep incrementing that number. So this, all it means is +1. So you keep incrementing it, and you get successive numbers. Okay? So that is one way to get a pseudo-random number stream, basically. This would be a whole sequence of bits. And the way you just use it to encrypt anything is, okay. Alright, so this should be clear by now that this is basically, you take a number and like a counter, you just take counter and then keep incrementing it. Is that clear? Right? Then this one is this is counter mode, and this is OFB mode. In the OFB mode, you just take the output feedback as a new value and encrypt it so that we keep getting this stream. Yeah. Yeah, if you use from one, then that will be known. Basically, the first of all, the key is not known, right? Oh, no, hold on. Let me see. Let me explain to you how to do it. So you have plain text, which is 0 and 1, and you have this stream, which is 0 and 1, and you exclusive are it, and you send it out. Right? That's how it works. Now, so there's no plain text shown here in this picture. This picture simply shows how you get that pseudo-random stream. Alright? Now, pseudo-random stream can be regenerated at the destination if they know the initial value of the counter and the key. If they know what? If they know what?
If they know the initial value of the counter
and the key.
Well, who can figure out the key by, you know, like, they know the syntax of, like, where the counter starts, and they know what that produces. Can't they then work back to find the key?
Okay, so let me see. So you are saying that they know the ciphertext and they know the plain text. They can exclusive array and get this stream. Okay, and then what?
Well, if they know what the counter value is at that point, can they work back to find the key?
No, see, that's the thing. That's the thing. Given the plain text and the ciphertext, in this case, all you know is the initial value maybe, and you know the pseudo-random stream, you cannot find the key. Both DES as well as AES, that's what we say that for DES you will have to do 2 raised to 54 operations to get that 56-bit key, right? For AES, if you are using 128, you will probably have to do 2 raised to 128 experiments to find the key. And that's the whole thing about those encryption thing, is that finding key requires so many operations that you won't be able to do practically. Right? So here, yes, if you know the plain text and the ciphertext, then it's very easy to find out the stream that you used. You just exclusive of the two and you get the stream. But given that stream, you cannot find the key. Is that clear to everybody? Right? It is very easy to find the stream, but that stream doesn't help you because you cannot use it again. Why you will not use it again? Because you will not use the same value again and the same key again. Right? We will use it for that message, for the next message totally different, something like that, right? So that is counter mode. The next one is output feedback mode, the same thing. Basically, you start with a value and a key, and whatever comes out, you just do it back. And you can use other modes as well. So we talked about 4 or 5 modes in the last lecture. Any of those modes can be used just without any message to generate a random stream. Any question about that? All right. You can also use, now this one is a standard for pseudo-random number generation, X9.17, and this uses 3 triple dash blocks. So EDE is 1 triple dash, EDE is another triple dash, and EDE is another triple dash. There are 3 of them, right? And you use 2 keys. For triple dash, you need 2 keys, right? Everybody remembers that one? That why don't we need a third key? Right? We encrypt with K1, decrypt with K2, and then encrypt with K1 again. So triple dash. So that's how you use 2 keys here, and you put your date and time, and you put a seed. So if you use the same seed again tomorrow, it will be different. Right? And today doesn't look like it. Okay, what is this? I don't know. It's today is not. Hopefully. So yeah, basically, so what they have done is they take the output of the encryptor, and that becomes the next value. So this VI plus 1 simply goes back here. So this is the feedback loop right there, outside external feedback loop. And inside, the date and time modifies the seed, okay? And also basically affects these 2 random number generators. This is a little bit more complicated than straight one EDE or one AES, but this is the standard for generating pseudo number generation. Another one you could use is natural random noise, which means that you could do something that is naturally random. I mean, say for example, something vibrates, or something which is like a what do you call the radiation. Okay, something radiates, and the radiation is supposed to be random, and you just measure it and then use that. So best source of natural randomness in the real world: find a regular but random event and monitor. So from radio noise, audio noise, thermal noise, radiation counters, capacitors, leaks, and so on and so forth. So there might be, actually, I mean, there's a danger in using these, because if you use leaky capacitor, you don't know that it is truly random or not. It could be that it is just, too much concentrated in one area. Who knows? But that is one possibility. And nowadays they make this hardware in new CPUs as well, so you could get some. So for example, in some CPUs they have TPM, the trusted platform, secure systems. So they need some secure ways to generate pseudo-random numbers. They might have such things where they randomly generate in the hardware. Now, so that is the problem. Problem of bias. Bias means that it is not totally fully distributed. It could be in one area. So uneven distribution. Have to compensate for this when sample, often by passing through a hash function. So basically what you do is you don't just take the number as it came out, you randomize it further using a hash. And best only to use few noises bits from each sample. So basically what you do is, if you get a sample which is this big, you don't use all the bits. Generally the noisiest bits are at the end, at this end, but this is not always the case, by the way. But at the least significant bits, maybe most noisiest bits. And in some cases it could be most significant bits. So you just use some bits. Anyway, so these are different ways of getting pseudo-random number generators. I have, in particular, in my personal ways, actually we have never used the other ones. We just use these kinds, ones which are mathematical rather than natural. So now, finally, we're going to talk about how to use these streams, and it's very simple. You take your random stream, you take your plain text, exclusive OR, and send it out. Very simple. And at the other end, you generate the stream, exclusive OR, and you get the plain text back. Okay? So unlike the block cipher, which had 10 rounds and 16 rounds, here there is only one. So all that complexity goes in here, in generating the stream. But once the stream is generated, you just exclusive OR it. So I'll give you an example of one of them, RC4. It is no longer used. And RC stands for reversed cipher. Now Ron Rivest is a famous guy in security. He owns the company RSA, Rivest. SA, I forget the name. SA is another person, A is another, 3 people. So RSA, is the security company, most famous security company. So this guy is a professor at MIT. And so he invented this one, RC4, and actually after this was broken in, then he invented RC5, then RC6. So there's a whole series of these. But just to get an idea as to how this works and how these things work, I will show you RC4. So this is a proprietary method which they actually is by RSA, yeah. So RSA company actually used this in their products, but they never disclosed the code. This is how it works. But somebody figured it out and published it on the net, so we all know now. So this is a round-reverse design, simple but effective. Variable key size, byte-oriented stream cipher. So basically, you can give it any size key, and then we'll give you a string cipher that you can use. And it is widely used in web, SSL, TLS, wireless web, WPA, and so on. Now, by the way, all of these things are also moving away from RC4 into, so it was used in web, which is the older wireless. In WPA version 2, they use AES. Okay, so people are moving away from this, but this was used. Key forms random permutation of all 8-bit values. So 8-bit you get 0 to 256. The keys would be, as you will see in a minute, all possible values are used. Uses that permutation to scramble the input. So let me show you how it is done to scramble. So you start with 256 counters. Okay, so this is 1 byte counter, and actually I shouldn't call it counter, registers. You start with 256 registers, each 8-bit long, so each 1 byte. Okay, first register is set to 0, 1, 2, 3, 254, 255. Okay, so 255 registers, just sequentially numbered, and the content is also sequentially numbered, right? Then you take your key. Your key, you put it as 1 byte at a time into 256 register. If your key is less than 256, you repeat it. So let's say your key is 128 byte long. You repeat it twice. You get 256 bytes. If your key is 64 byte long, you repeat it 4 times, and so on and so forth. If it is 123 byte long, you just repeat it as many times until you get 256, and you're done. Throw away the rest. So, everybody understands how these 2 sets of registers are initialized? First set is simply a sequence number from 1 to 255. Second set is your key repeated as many times as needed to make 256 bytes. Clear? Nobody's shaking hands, so it's not really clear. So in this method, RC4, we use 256, actually times 2. We use 512 registers. First 256 registers are this, something called S, and the other 256 are something called T. T has the key. Okay? And the key is, if it is shorter than 256 byte, we just repeat it until we go to the end. All right. Once we do that, now we do permutation. We just jumble up these registers. Okay, shuffle these registers. So how do we shuffle? Using these 4 lines of code. So the RC4 is designed for software implementation, using byte level manipulation, because they didn't want to do it in bit level, and they didn't want to do very complex what we call those multiplications that we saw, Galois field, 2 raised to n, things like that, right? So this is very simple. So all you do is, when you run this 4-line code, it says j equal to 0 for I equal to 0 to 255, j equal to j plus si plus ti mod 256. So you take the contents of ith counter here in S, and now ith counter here in T, and you add up those 2 plus j. J is the sequence number. Okay, you add up, you get a new value of j, and then whatever value of j comes out, you swap these 2 registers. So si value goes into this register, jf register, and sj value goes to the ith register. Okay, so it says that calculate which register I should swap. That value is j equal to j plus si plus ti, and then you swap si and sj. Now next time you will come back with I equal to 1. Now the new value of j will be calculated, and then s1 will be swapped with that one. And then you will come back with s2, I equal to 2, calculate new value of j, and you will swap that. So the swapping will depend upon the key, because if t is different, the new values of s will be different. Okay, so what we have done so far, we have taken 256 registers which had value 0 to 255, but depending upon the key, now they have been jumbled up. Okay? Does that make sense what we have done so far? We have just moved the bytes around depending upon the key value, because T is the key. Remember, this T is dependent on the key, and S is just a counter. So now the S values are all shuffled, right? Now we can start encrypting. And encryption is very similar to what we did a minute ago, is that we start with I and j equal to 0, and we increment I, and we calculate j is equal to j plus si. Now there is no ti here. J plus si, and we swap si and sj. First we do the swapping, then we add them and calculate the t, and st is what we return as the next byte. So basically, this value st, whichever comes out your calculation. By the way, everything is 256, not 256, because there are only 8 bits. So if you add two numbers and they become more than 256, the 9th bit will flow out anyway with overflow. So you don't care about that. So you get 256 values. All values are between 0 and 255. So you send out the st, the TS counter, as your next 8 bits. We call it key here because that is what you exclusive are to your plain text. If you are given 1 byte of plain text, you get this 1 byte and you exclusive are and send it out. And then when you come next time, you increment I, calculate j, swap si and sj, calculate t, and then send out the counter for st. Alright, next time you come, again increment I, calculate j, swap si and sj. So every time you're shuffling the deck, shuffling these 256 cards, and then taking out a card and saying, oh, here's a random number. Okay? Getting some idea of this or not? Okay. All right. So RC4, so this ends this chapter. Actually, it was a very short chapter. All we did was we told you how to generate pseudo random numbers, and then we talked about how to get a stream, and then we gave an example, RC4. Any question about pseudo random number generator, RC4, or anything? Now, homework is related to RC4, I think. Let me see. The homework is 2 parts, A, B, C. A part is related to LCZ. So you need to figure out what the value would be with C equal to 2. First C equal to 1, and then C equal to 2. You will find out that the period, and if you remember what the period is, a period of this generator will depend upon the seed. Period is cycle length. Okay? So figure that out. And then the C part is related to RC4. Now this is kind of not trivial actually. Find out what key value will leave S unchanged during initialization. So, during initial permutation, just to be clear, I made this thing, initialization might think that, okay, initialization, nothing is done. You just initialize to 0 to 255. So that is, after initial permutation of S, the entries of S will be equal to the value 0 to 255 in the ascending order. So here's the thing basically, is that what value of key should be this Ti, so that when you add and swap Si and Sj, at the end it will just come out the same value. After all the shuffling, it will still be 0 to 256. It will not be 0 to 256 at every step, but after 256 step it will be same. So basically every alternate value maybe bring it back to the same position, something like that. Okay? So you have to z equal to 0, 0 to 255, you do it, and then you know, if you do it to 56, the end value would be 0 to 256. Is the problem clear? It is just for the initial permutation, not about the encryption part. I mean, here, by the time you come here, it will be different. But so that is the C part. A part and B part is very straightforward. All you have to do is put x naught equal to 1, calculate, and 2 raised to 5 means 32. So all the number will be between 0 and 31, right? And as soon as you get the x equal to 1, you know that the cycle has finished. And you get the cycle length. Here you start with 2 and you get the cycle length. So this is very straightforward. I think you can do it even here. So anyway, so this is that, right? Any question about chapter 7? If not, we go to the next chapter on cryptography.